In Unit 3 on Topic 2, Electromagnetism, we're going to start by looking at Coulomb's law, but before we do, I want to just refer back to Unit 1, Topic 3, and these three dot points in particular. Recall that electric charge can be positive or negative. Recall that electric current is carried by discrete electric charge carriers, being electrons, and recall the law of conservation of electric charge. So while that's Unit 1, Topic 3, it does underpin what we're doing here with Unit 3, Topic 2. So I just want you to make sure you've got that in mind as we can start going through this content. In order to make sense of that, what we're going to do first of all is just restate some of those particular aspects. And we'll start by identifying that charge is just simply a property of matter. So it's not something that's really easy to explain when you sort of get down to it, other than to say that it's a property of matter, the same way that mass is a property of matter. And that property causes certain phenomena. Two of those phenomena that we'll deal with are the idea that like charges repel and opposite charges attract. So we'll have a look at that in a little bit more detail as we go through this idea of Coulomb's law. There are other phenomena that we'll see as we go through this topic, but we'll start off with those two to begin with. Now, when we're talking about charge, we also need to identify how objects become charged, and so that's by considering the transfer of electrons. So an object becomes charged either by losing electrons, and if that substance has lost electrons, that means it's going to become positively charged. So if it loses negatives, then we're going to see positive charge in excess, or by gaining electrons. So note that, as we referred to earlier, the charge carriers that we're dealing with electrostatics are electrons. So it's not the positive charges that move; it's the negative charges that are either gained or lost, and as a result, we see something as either being negatively charged or positively charged. Now, we also saw that conservation of charge is an important thing to keep in mind as well. So if one object loses electrons, another object somewhere is going to gain those electrons. So we can't just have charge being built up in isolation. Another thing just to identify here as well, objects usually fall into two different categories. And those two categories are insulators and conductors. So an insulator is one that doesn't allow charge to flow through it, and as a result, what ends up happening is when a charge is built up on it, that charge will be localized. And I'll draw a diagram here to represent that situation. So just to make this note, excess charge is localized. So when we're dealing with insulators, we're dealing with things like glass or rubber, so two examples there. Lots of others that we could refer to as well. So if we consider an insulator, we're looking, say, at an object, let's say it's spherical. Changes when you're looking at objects that are different shapes, but we'll just start with something that's spherical. So in that situation, the charge build-up might only be on this region of the object itself. So the charge hasn't been distributed across the surface, it's all built up in one region. The other one, as we said, was conductors. And now conductors allow charge to flow through them. And as a result, that means that the charge can sort of be pushed apart. Excess charge will be distributed across its surface. And the reason why it's across the surface is that it's going to be sort of pushed as far apart as possible. And in the case of a sphere, it's a special case, so we'll just deal with that, but you could do a whole lot more detail on the different shapes of conductors. Example of a conductor there, as well as anything that's metal. So if we have that shape of a sphere again, then what we're going to see with a sphere is that the charge will actually be evenly distributed across its surface. If it's not spherical, if there's sort of points to it, then that charge won't necessarily be evenly distributed, but it will still be across the surface. So you can see the difference between this diagram at the top and the diagram at the bottom, localized charge compared to evenly distributed charge on a sphere. Now, getting to the important point of this video, we're going to now look at Coulomb's law. So the idea of Coulomb's law builds on this idea of objects being charged. Coulomb's law describes the force that exists, or the electrostatic force, and that can either be a repulsive or attractive force, so either of repulsion or attraction, and that force is going to be between electrically charged objects. Now, in trying to explain this, we're basically just going to go straight to the sort of the textbook definition, and the idea is that we're just looking at the force itself. So this force, there's three things to keep in mind about it. The order that's listed in the glossary in the syllabus is not quite the order I'm doing here, but it's all the same 3 points. The first thing is that it's directly proportional to the product of the two charges involved. So we're always going to be dealing with at least two charges. If you've got multiple charges, it becomes a situation of having to sort of add the forces together. In the case of two charges, we're just looking at one force that's existing, and so we'll start off there. So directly proportional to the product of the electric charges, and that means that we have F being proportional to Q multiplied by Q. So lowercase q to represent one charge, capital Q to represent the other. It'll become apparent why we're using those two letters and not just Q1 and Q2 a bit later. The second thing then is that it's inversely proportional to the square of the distance between the charges. So as we see a lot in physics, we've got this inverse proportion, but not just an inverse proportion, inverse proportionally to the square of the distance. So that idea of an inverse square proportion happens quite a lot, and we're not going to get into the detail here of why it's an inverse square, but think about the idea here. If you move two charges apart, if you sort of moved any distance around that, you're on the surface of a sphere, and that sort of then starts to relate to the area, and area is related to the square of a distance. So here F is proportional to 1 on r squared. The last thing then, we've kind of already stated it, is that that force is going to be attractive for opposite charges, and we'll have a look at how that makes sense when we get into the equation. And it's repulsive for like charges. Now, if we take all of that information and put it all together, we get an equation that usually you'd see it in this form. So I'm going to start out with this equation, but then I'll develop it into the one that's in the data booklet. So F is equal to KQQ on r squared. So we've got the product of the charges in the top, QQ, and then the inverse square, so divided by r squared underneath. That value of K is the constant of proportionality. So we have the F is the electrostatic force in newtons. So just listing out what each of these quantities are. And the values of Q and capital Q are the charges in coulombs. So charge being measured in the units of coulombs, Now usually the charges that we'll deal with will be sort of microcoulombs, so 1 coulomb is a very large amount of charge, so quite often it'll be micro or even picocoulombs. And then r is the distance between the charges, and that will be in meters. Now this value of K, it's known as Coulomb's constant, and the value itself is related to another property. So with Coulomb's constant, it has a particular value, so K is equal to the 9.0 by 10 to the 9, and the units of the constant are Newton meters squared per Coulomb squared. And that's actually equal to the quantity 1 on 4 pi epsilon naught. Now this epsilon naught quantity here, that's known as the permittivity of free space. Now it's not something that we actually need to cover in the syllabus, so I'm not quite sure why they've decided to represent the equation in this form, but just to note it here so you're not confused by the representation in the equation. Now the permittivity of free space, it's basically just a quantity that talks about how easily an electric field will be formed in that region. So if we're talking about free space, we're talking about a vacuum. But like I said, don't really need to worry about that level of detail for what we need to know for the syllabus. The only reason why I'm mentioning it here is because we then have the equation in this form. So instead of writing the value K, we're going to write that value 1 on 4 pi epsilon naught, and then we're going to multiply that by Q, capital Q, on R squared. And that's the equation that you've got in the data booklet. Strangely, they've actually got this value in the data booklet as well. So they don't use the value K, they use 1 on 4 pi epsilon naught, and then it's given the value of 9 by 10 to the 9 Newton meter squared per Coulomb squared. So that's Coulomb's law. We'll have a look at some problems in class, but one last thing I want to identify here. We mentioned that Coulomb's law is directly proportional to the product of the electric charges, which is stated in the equation here. We also mentioned that it was inversely proportional to the distance between them, which is this divided by r squared aspect. The third thing we said is that it's attractive for opposite charges, repulsive for like charges. Now, if we consider those charges, so I'm just going to sort of tabulate them here a little bit. So if we've got the two charges, Q and capital Q, and we're going to look at how they contribute to the force F. Now, if we're just looking at the signs, if Q is positive and capital Q is positive, when we substitute into this equation, Q times Q is going to be a positive answer, so the force itself is going to be positive. Likewise, if Q is negative and capital Q is negative, multiply two negatives together and we still get a positive answer. So we can see there that if the force has a positive value, then we know that it's going to be a repulsion. On the flip side, if lowercase q is positive and capital Q is negative, then multiply a positive and a negative together and you get a negative answer. If lowercase q is negative and capital Q is positive, similarly we're still going to end up with a negative answer. So if we get a negative answer, that means that the force is going to be attraction. So there's Coulomb's law. As I said, we'll do some problems in class looking at calculating the force or figuring out how far apart two charges are for a given force. We'll spend a bit of time making sure that we've got that calculation under control.